My name's Andrew Binley and I'm based at Lancaster University, UK. I'm going to give a talk today on efficient multi-scale imaging of subsurface resistivity with uncertainty quantification using ensemble Kalman inversion. This is a supplementary talk to our PICO presentation in the Advances in Geophysical Imaging of Near-Surface Structures and Processes at EGU 2021. So I'd like to first acknowledge my co-authors, Michael So, formerly of Lancaster University, now at UKCH, Marco Iglesias at Nottingham University, and Paul Wilkinson, Oliver Couras, and John Chambers, all at British Geological Survey. I need to stress from the start that the work I'm presenting here was really led by Michael, with a huge amount of input from Marco. What I'm going to present is a new inversion method that we've developed, which allows us to look at sharp interfaces. And we're going to demonstrate the improvement that we get when compared to a conventional smoothness constrained inversion for resistivity problems. The inversion is based on a level set parameterization using spatial hyperparameters that are inverted with an ensemble Kalman inversion procedure. And we're going to demonstrate the method for resistivity for a series of 2D and 3D synthetic and field examples. And as I said, we're going to compare these with a conventional smoothness inversion. Let's look at the motivation. In many problems that we look at in near-surface geophysics, we're interested in identification of boundaries, units, layers, zones, and so on. So they may be lithological units within the subsurface. It may be a solute plume that we want to identify, maybe estimate volumes of particular regions, differentiate permeable units, for example. Smoothness constrained inversions are often not well suited for that kind of problem. In addition to this, we recognize the need to provide some estimation of uncertainty in our models. There has been a number of attempts to use Markov chain Monte Carlo solutions for these kind of problems, but they can be very expensive, particularly for very large problems. An important aspect of looking at zonation of regions is that if we want to get quantitative information from our inverse model, let's say we want to get values of resistivity or chargeability for an induced polarization problem, and we want to convert those into some property, let's say permeability or a solute concentration, then getting an accurate estimate of the properties of these regions is really important. And so I'm showing here on the right a idealized case with 4 zones, and if we apply a conventional smoothness constrained inversion, then we get these smeared results as we'd expect. But if we apply some boundaries to our conventional smoothness constrained inversion, so we switch off regularization along these boundaries, we see we get improved estimates of the values of resistivity in this case in these regions. So if we want to convert those resistivities to some property or state, we can see the value here of actually enforcing some zonation. And we want to build on this in this study by coming up with an alternative approach to inversion, which automatically finds these boundaries. So as I said at the start, the method that we're proposing here is based on a level set parameterization. This gives us a flexible way of zoning arbitrary shapes. We break the problem down into solving for a series of hyperparameters that describe the spatial patterns and the zones. And we solve the problem using an ensemble Kalman inversion, which is an efficient Bayesian-based approximation that allows us to get some estimate of uncertainty. The level sets approach has been used in a number of studies, and in some it's been used where an explicit assessment of a sensitivity matrix, a Jacobian, is required, and that can add some computational burden to the problem. What we can use as an alternative is a Gaussian random field, generate a random field, and actually use some thresholding within that random field to define the zones. And so we show up on the top right here, this image showing how you might actually threshold different levels of our random field and result in some zonation, which does not need to be continuous. So we see on the top right here, we've actually got two individual zones that make up that single property. And we're going to use this approach here to allow us to zone our inverse solution. So we generate a random field, and for the random field we use the Matern covariance function, and as shown here. And basically it consists of a number of key parameters. We've got a smoothness parameter, we've got correlation length scales, and we've got variance. And so we show in the image here on the right, in the bottom right, how if we change the smoothing or if we change the correlation length, we see different kinds of structures. And these are thresholded in this example to show red and blue zones. So they may represent two distinct types of lithologies or solute concentrations, characteristics within our subsurface environment. So these are the hyperparameters that we actually wish to invert for, or they make up the set of hyperparameters, because there are some additional parameters that we need to look at here. We need to define a mean resistivity for each zone. So what we'll have then is a series of correlation lengths. They could be anisotropic or isotropic, and we've shown here the general case here for an anisotropic correlation length set. We've got variance, we've got a smoothing term, we've also got a white noise term, W here at the end, and we're going to define for each zone a mean resistivity. So there will be two additional hyperparameters if we decide to go for a two-zone solution, and three mean resistivities if we go for three-zone, and so on. If we want to consider heterogeneity within each zone, then we can add additional hyperparameters. So in addition to this set here, we can add for each zone an additional set of hyperparameters that will allow some variability within that zone. And I'm going to show you an example of doing this later. So the ensemble Kalman inversion uses an ensemble of realizations to search for the minimum of the parameter space, and it's done in an iterative manner. We don't need to calculate a Jacobian, we just need a forward model. So we need some way of calculating a set of apparent resistivities for a given resistivity distribution. Remember that we're solving for the hyperparameters U, and the hyperparameters will define the spatial pattern of the resistivity field. So we need to define the priors for the hyperparameters, and we need to make sure that the mean resistivity for each of the zones doesn't overlap. At each iteration, we map the hyperparameters to a resistivity field. So we generate a resistivity field from those hyperparameters, and we calculate the forward model for that resistivity field. We use a damping parameter, alpha, and we set that inversely proportional to the misfit. So initially the damping is very high and then it reduces over time. We define two matrices, the data autocovariance matrix and the model data covariance matrix. And these are computed at each iteration. So there's an example here from the literature which shows 4 ensemble members for a 2-parameter problem. And as they move in 2 iterations towards the minimum, and then we classify the entire response by this ensemble mean. And we can look at the variation in our final distribution of hyperparameters to come up with some uncertainty estimation. So the solution looks, the procedure looks something like this. We work in an iterative fashion. So we're solving for the hyperparameters U, and we at each iteration we calculate a step in our hyperparameters using our data autocovariance and our model data covariance matrices. We got our damping parameter here, and then we got this term on the right here, which is effectively a misfit term. So we step through until we consider that we've converged, and that gives us the final set of hyperparameters. Let's look at some example prior realizations for a simple 2-zone problem. If this is our true model here, we can look at here a number of realizations from a set of 300 in this case, illustrating different types of distributions of resistivity that come from a given prior distribution. So we need to start with these prior models and progress through in an iterative fashion until we get the converged solution. We work with 300 realizations in the examples I'm going to show today. That is constrained by computational limits. It does pose some restrictions on the accuracy of the resulting uncertainty estimations, and I'll refer back to that later. We can select 2 or 3 zones typically for our problems. We define our prior means. We set some convergence criteria, and then we can decide whether we want homogeneous zones or whether we want variation of resistivity within zones. The scripts that we've used are all based in MATLAB, and the forward modeling was done in 2D using the code R2 and in 3D using Tim Johnson's code E4D. The parameters were estimated on a rectangular grid and then interpolated onto an ERT mesh. And the ERT mesh is typically triangular for the 2D problem or tetrahedral for the 3D problems. That doesn't put a constraint on using complex topography, and I'm going to illustrate an example later showing that. And we're going to show some benchmarking and comparisons with the smoothest constrained inversion for the 2D problems using R2. Let's look at a simple synthetic problem to start with. This is a cross borehole example. So the true model here is shown on the left. We've got a resistive background, 100 ohm meters, and then we've got a very conductive anomaly in the center that lies between 2 boreholes with a string of electrodes in each borehole. The dots here indicate the electrode positions. And so when we run a smoothness constrained inversion on this, so we've generated a forward model, added some noise, done an inversion, we get a smoothness constrained response. we don't really see that object because it's too far away from our electrodes, too small, and the contrast is not high enough. When we use the ensemble Kalman inversion with this zonation, we pick up this anomaly as shown here, and the values are consistent with our known anomaly resistivity. We can look here at our posterior distribution, in this case for the zone 1 probability. So this is the background region, and we see the high probability in yellow and the low probability, i.e. that's likely to be zone 2, shown in the blue colors. So this is the kind of information that we can get from this solution. Let's look at a surface array problem here, where we've got a conductive layer over a more resistive layer. When we run the smoothness constraint inversion, we can see some contrast, but it's not very sharp. And we're limited here by the depth of investigation of our survey, and more significantly, in this case, we're limited because of the smoothing, additional smoothing, enhanced smoothing that we get at depth. So we get a much more smeared response deeper down in our profile. When we use the ensemble Kalman inversion solution, we identify this boundary very clearly. So we've got our resistivities here shown on the same color scale as the true model in the top left, and we see that we actually resolve the mean response very well. And we also pick up this boundary pretty well. If you look at our zone 1 probabilities down at the bottom, we see this zone 1, this resistive zone boundary is identified really close to the known boundary. In this example, we've got some variation of resistivity within our zone. So we've got two zones that actually have a variation of resistivity within them. So there's a clear boundary between the two, but there's also variation within the two zones. So this is more like a realistic case. And when we run this through with these additional hyperparameters then that capture the variability within the zones, and we see this kind of response. And so this is the ensemble mean shown here in the top right. And then if we look at our zone 1 probabilities again, we can see that we can still pick out some structure which is pretty similar to the known boundary. But clearly the variability that we've got within the zones adds some additional complexity to this problem. Now let's move to 3D. We've got a synthetic problem representing a electrically conductive abandoned mine shaft. So we've got infill soil, say in this mine shaft, in this vertical shaft. We've got surface arrays, 3 surface arrays, and the true model is shown in the left here. When we run a smoothness constraint inversion through this, we pick up this conductive unit, but we don't really see it as an extended vertical feature because of the limitations of the smoothing of the inverse problem here. However, when we apply the ensemble Kalman inversion, we see that we can resolve that vertical feature really quite effectively. And again, we can illustrate this with probability maps to indicate the likelihood of that zone occurring within our region. Now let's look at some field examples. And the first one I'm going to start with is a nice simple example with a fairly flat horizontal profile. So this is a peat bog on the west coast of Wales near the village of Borth. And at this site, we've been carrying out a number of investigations to look at the structure of the peat bog. And on the on the bottom here, I'm showing a GPR profile, which clearly identifies the base of the peat here, where we and the top of a clay unit. But the peat itself consists of two main units. We've got the peat on top of a very decomposed, organic, rich layer, which has completely different properties to the peat above it, and you can see that from the scatter that we get in the GPR profile. So it's a much more uniform, heavily compacted, organic rich layer which sits on top of the clay. So we see this horizontal structure within our GPR profile, and that's being confirmed by augering within the site. But if we look at the resistivity responses, when we look at a smoothest constrained inversion on the top here, we see a gradual transition from a more resistive to a more conductive layer, as you'd expect from applying a smoothest constrained approach. When we run the ensemble Kalman inversion, we get this sharp contrast, and that occurs around about 5 meters depth. If we go back and look at our GPR profile, then that seems to coincide with the bottom of the peat layer. So it's consistent with our GPR and our auger survey. We cannot differentiate between this organic rich and the blue clay layer, but what we can do is we can differentiate between the peat and the horizon beneath. If we look at our probability maps, we see here the zone 2 probability. So the likelihood of this lower layer is again showing the demarcation of this of the bottom of the peat. So the next field study site is in southwest China, and this is a karstic environment, complex karstic environment, where we're interested in the structure, the hydrogeological structure of this environment. And ultimately, we want to know how vulnerable the area is to land use change. And kind of key to that is the development of a hydrological conceptual model of the site. And that is underpinned by a good geological and geophysical characterization of the region. And so we've been carrying out a number of geophysical surveys, and this is one that we're going to focus on, which is this hill slope profile along a 250 meter section that goes through different land uses here. You can see this forested area, there's some terraced area, and then these managed plots down at in the valley bottom. And we've run geophysical surveys over here to look at variations, in this case in resistivity, and how that might map to soil and bedrock characteristics. So this is a 48 electrode survey that I'm showing here, 5 meter spacing. And when we run a smoothest constrained inversion, we get this variation in resistivity. And when we run the ensemble Kalman inversion, we get a similar pattern, as you would expect, but it allows us to actually see some demarcation of zones within there. So we might attribute the yellow zone here, the high resistivity zone, to solid bedrock, and then we've got 2 other zones within here which may be characterized by weathered bedrock, or maybe infilled soil, or they may be more conduits within there that actually have some infill or fluid within the channels. So it allows us to come up with some zonation then of the different geoelectrical properties of our system, and we can look at the distribution of our resistivities within each zone and see how they differ and how they may relate then to known properties, physical properties of the study site. In this final example, we're going to look at a well-characterized site near the village of Eggborough in the UK. And this is a site that we studied some time ago. And we picked this site for this illustration because we've got a lot of independent measurements that allow us to compare our resistivity inversion with other data. So this site is an unsaturated sandstone down to about 17 meters, and the sandstone consists of a number of layers within this mass. Consists of some fine sandstone and siltstone, as well as medium sandstone, and that gives us some kind of horizontal structure within the unsaturated zone that we've been interested in how this layering has an impact on recharge processes to the water table, and actually ultimately how the transport of potential contaminants near the surface can move through to the water table. So, as I said, we picked this site for illustration here because we've got a lot of other data that we can compare against. We've got gamma logs in boreholes, we've got EM logs in boreholes, a well-characterized core, as well as some cross-borehole ground-penetrating radar. So when we run an inversion, this is selected two boreholes, data collected between two boreholes. When we run an inversion, in the top right here with the smoothest constrained inversion, this is with a normal isotropic smoothing, then we get some kind of evidence of some layering within there. So we've got two boreholes down to about 16 meters, 10 meters apart. We get some kind of layering within there. If we force the smoothing, our regularization, to be horizontally enhanced by a factor of 10 to 1, then we really bring out that layering, but we've kind of forced that without any real justification, but we can bring out some of that layering in there. When we apply the ensemble Kalman inversion, then that automatically brings out this zonation, and you can see in particular you've actually got this layer about 5 meters depth, which has come out as significantly different to these other zones. As before, we can look at the zone probabilities, and that allows us to look at the reliability of these from an inversion perspective, the reliability of these demarcations. But let's look at how these compare with independently observed observations. So if we've got our image zone here between these two boreholes, E3 and E4, we've got two boreholes in between them, R3 and R4, which we use for ground penetrating radar. So cross borehole ground penetrating radar carried out between these two boreholes, and we see this GPR profile, and this brings out this low velocity, i.e. high water content zone at 5 meters, which coincides nicely with this different zone that we've got out with our ensemble Kalman inversion. And if we look at our gamma profiles, we can see that we also get variations in our gamma counts, which we will link to clay content, that also show consistency then with our zones that we've picked out from our EKI solution. We've got to remember that resistivity is going to be a combination, is going to be influenced by not only the clay content, but also the water content, which in turn is influenced by the clay content. but near the surface, even though we actually don't get necessarily a high gamma count, because it's near the surface, we've got a high moisture retention there. So that's why this zone actually at 5 meters stands out much more strongly than, say, this zone at, say, 12 meters depth. But from these radar and gamma logs, we can provide some explanation of the zonation that we've got and confirmation of the appropriateness of the zonation that we've got from our ensemble Kalman inversion. Let's look at computational performance. Well, the problems that we've run here are much more computationally intensive than a smoothness constrained inversion. And in fact, the procedure that you would probably follow would be to carry out a conventional smoothness constrained inversion and then use that to guide the number of zones, the suitability of using some zoned inversion. The runtime is dominated by the size of the forward problem, but we can add some parallel computation in there to actually make the solution much more efficient computationally. We've run all the 2D cases on relatively modest computer platforms, but the 3D case needed something a little bit more substantial. But we're running solutions in the order of 2 to 3 hours for the kind of problems that we've shown here. So we're not relying on really extensive supercomputer resources to be able to solve these kind of problems. So in summary, we've shown here a flexible and an efficient alternative to smoothness constrained inversion, and also the so-called L1 inversions, or the pseudo L1 inversions, the blocky inversions. So we provide uncertainty estimates here, which is a great bonus for this kind of approach. So the ensemble Kalman inversion is a low-cost sampling-based Bayesian inversion, derivative-free. We don't need to form a Jacobian, and it has this really immense value of being able to get some uncertainty estimation from our final model. We use a level set parameterization, which is useful to estimate sharp interfaces, and we can add some heterogeneity within that zonation as well. And we demonstrated this for 2D and 3D examples. The zones that we've used here should be non-overlapping with our prior resistivity ranges. So that's a condition of the approach that we're taking here. We can't have an overlap. There must be some kind of threshold if you think about these Gaussian random fields. The uncertainties that we used were derived from only 300 realizations. So we have to use them with care, but they are probably going to be more reliable than any uncertainty estimates that come from analysis of smoothness constrained inversions. We specify sharp interfaces, and so it's possible for it to resolve a gradational interface as a sharp one. So we need to think about this when we perform this kind of inversion. We're enforcing a sharp interface, but it might be in the real problem that there's more of a gradual interface. And an obvious one would be a water table boundary in a fine textured soil would not be expected to have a sharp interface, but we are going to enforce a sharp interface with this kind of solution. We could apply, in theory, this approach to time-lapse data, and that's actually something that we're considering currently. In other words, using the change in resistivity as the structure that we're solving for. We can also extend to induced polarization, and the black box nature of it means extension to coupled and joint inversion is actually relatively straightforward. So I've really just summarized the general principles of the approach here. But for more information, I encourage you to go and look at the paper that Michael So laid on that has just come out in Geophysical Journal International. There's a DOI link here, and in addition, there's a DOI to some codes for you to download and explore with if you're interested in pursuing this further. Thank you.